We will be explaining little more on structural designing of a glass and glass facade. Previously we have covered mostly on application side, various forms of application. Here we will be taking through little basic structural designing of a glass facade. The key design basis of the glass facade is primarily defined by two things, primarily strength and sometimes governed by deflection criteria. And moreover, to strength and design, there are instances covered by building movements like such as could be earthquake or thermal movement or any type of building movement. And the basic design principle is designed for it's like any other structural design like steel design or concrete design. The design philosophy is similar, it's only the material character is changing. So it should be designed for safety and designed for serviceability, and design approach is when we do the design factors are wind load factor, load factor, live load factor. There are different factors is considered with suitable combinations, and in some instances the design need to be checked for non-linear. Non-linear is critical if you are doing a slender elements, small size of the glass fins, it is used for large spaces. The slenderness ratio is too small, then slenderness factor is critical. The framing design. So the first thing we start with the facade design or glass design is the primary member which is supporting the glass in place is a framing. The framing is designed primarily like any structural elements like aluminum or steel, and how the framing is done, how it is getting fabricated, what is availability which define the design. And design of glass facade designs primarily like you're assuming the wind load or calculating the wind load, and you are checking the thickness of the glass material or supporting frames, and you are checking for a stress analysis, and there are instances you will be checking for a specific applications like a skylight application or hand railing, glass railing application where it has to be considered for human impact load. So it depends on the application. And in terms of glazing and fixtures, it's supported sometime by framing, in a way sometime it's supported by just a point fixing. So we should be mindful of how it is supported. The four factors we primarily checking for a facade design: strength, make sure it is safe and it has adequate safety factor; deflection, and to make sure it is deflecting and it is working in still serviceability and safe to accept the deflection; seismic, earthquake or some more natural climatic conditions; and building movement. So this is more critical for a large building, tall building, a slender building, using curtain wall glazing where the glazing is spreading across the building, where this building movement is more critical. We are going to explain more on strength aspects of the facade or glazing design. This is primarily applicable for supporting framing elements of facade structures. Like a framing element is, in most of the cases, it is either steel frames or aluminum frames. So we have the designer need to check for tension, compression, torsional, or in many cases combination of all these three aspects. Tension is, yes, you have a pulling force of this member. Compression is, it's like a column design, the struts are getting compressed. So in this case you have slenderness factor is more critical. And torsional is in many cases is critical if the building individual floor height is like 4 meter or 3.5 meter and it has a large span of unsupported length where torsional is critical. And shear, primarily checking for fixing connections and brackets. And in many cases the curtain wall or glazing member subjected to combined action of tension, compression, torsional, or it could be compression and torsional. So the designer should able to understand clearly that action and where is this check is critical. Bending check, Primarily, bending check is applicable to the framing elements which is supporting the glass panels. It could be vertical framing elements or horizontal framing elements. The bending theory is same, any beam bending theory is applicable. It depends whether this member is simply supported or it is continuous. If the glazing system is going only from floor to floor, it is not vertically continuous, then the members can be designed as a simply supported bending element. So, most of the cases, in that case, if the beam is vertically supported, it is simple bending theory like WL square by 8 is applicable, which is a bending check. Bending check is we are checking the compression and tension to make sure the member is structurally safe for both criteria, because if you check for positive and negative wind load, the member need to be checked on both directions. This is check is critical for compressive and tensile check. This is critical for a large element, or maybe sometime the framing is used for continuously for quite a number of floors continuous. There compression is critical. Compression is critical, as a structural engineer knows, when certain elements is weak in slenderness ratio. So, as engineers, they have to check the slenderness ratio. If that falls under like a semi-compact or slender, then this more detailed check is required. Shear check generally check for connections, brackets, where the components loads, large loads are transferred in a small component, where this kind of a shear stress is critical. This is critical if that especially using aluminum brackets. Aluminum brackets has slightly lower bearing stress and bending stress compared to the steel. So, this checking is critical for facade and glazing applications. This is local buckling check is critical in glazing system. Most commonly the elements used extrusions or aluminum framings. It has a thin wall thickness like 1 mm, 0.8 or 1.5 mm thickness. In these cases, this buckling check is critical, because it is quite common to use slender elements on facade systems. In that case, it could fail in local buckling, or it could fail in overall buckling, or it could fail in combination of local and overall buckling. So, there are detailed checks with various standards available to do the buckling check. The buckling check is critical on most of the facade systems. Overall buckling check is something similar to the steel design. If you are comparing to the I-beam or open section C channel, it is not a closed section like a hollow section. In this case, is similar to the steel bending theory. We have to apply this to the aluminum design. There are checks available based on slenderness ratio. If the slenderness ratio is very small, then it is critical to check the buckling check. Similar to the steel I-beam design, the buckling check has a different formula to check if it is a compact section, semi-compact, slender element. Depending upon the aspect of this member, there are various formulas is given in analysis codes. We have been so far checking for strength. Here we are checking for a deflection. A deflection check is critical to make sure the member is deflecting as what engineers is assuming, and this is going to be deflecting for wind loads, or sometime it could be for live load. So, the members, glass and glass elements need to be checked for these different criteria. Is primarily driven by the wind loads, could be negative wind load or positive wind load. Here we are checking for deflection. Deflection check is needed for glass and glass supporting framing elements. Deflection generally follow the beam deflection theory for framing elements, and for glass checking it follows the plate analysis theory for glass checking. The beam deflection theory, it could be either continuous beam or simply supported beam, or if it is more complex, it requires a computer analysis, so that the behavior of the beam is able to predict correctly. Like any other structural element, there is allowable deflection criteria is specified. Allowable deflection criteria is specified mainly for serviceability conditions, aesthetic conditions, as defined in the design of these elements. And actual deflection is predicted, then the engineer need to check actual deflection is within the allowable limit, then this framing elements or members is considered as structurally adequate. We will be talking little more on other impact of this facade or glazing system. This one other aspect is natural conditions or seismic. It could be different things like building movement on many different aspects. In particular to seismic, how it impacts the facade system, we can study little more detail. The seismic has many different impact on the facade. As we all know, the seismics induce a lot of building movements. Sometimes the building is accelerated too fast, and the materials which is attached to the building may not able to sustain or take these additional loads. And it could be imposing, the seismics could be imposing on a very tall buildings like interstory drift or sway beyond the limits. And seismic could also impose a lot of differential building movement. It's like one floor is not moving, the upper floor or top floor is moving too much movement, and the seismics put a lot of dynamic load to the building envelopes or framing or glass element, and it also give so much of additional loads to the serviceability of this framing system, bracket system, or the glass or cladding panel which is supporting. Continuing with the loads relevant to the building movement or could be seismic or earthquake, the predominant force which is imposed onto the glass panel or facade system is in-plane forces. What you can see here, when the building is drifting or swaying, it is going to put the horizontal loads on this glazing element, and this system need to be verified for in-plane load. As structural engineers should be aware, the facade system or its material is a very strong element in supporting the out of plane loads like a wind load which is acting on a plane. It may be weaker on its own plane on this minor axis loading. So the building sway may impose minor axis loading which need to be checked during the design. Here we are explaining other impact of the framing, how the framing will perform if the building is swaying or drifting. It could be due to earthquake or due to the just a wind load or sometimes even a gravity load. So the building, high-rise building, we all know it will sway on it due to the height of the building or slenderness factors of the building. But this building sway, how it will impact on the glass facade. If the framing, it could also give a various modes of acceleration. The frame could have this kind of impact, or it may be linearly leaning towards this. So when the frame moves, it will put a lot of stress on the glass panel or any other cladding material which is holding this. As a structural engineer, they have to check this. Here we could even little more detail a video showing how this building sway will impact the framing elements in particular. As you can see the building swaying, when the framing changes to red, it is highly stressed. As you can see, this frame is imposing a lot of loads onto these members when it is swaying. You can see here, which is this video is showing primarily this linear sway condition. This condition, the frame will have more impact relying on the weaker axis bending. Continuing with the building movement, the facade system, you can see a typical section detail of the facade system, the glass here, and it has a framing arrangement, and there is a bracket which is holding these panels. So this is a primarily, if you take a curtain wall glazing system for a commercial building, generally this system is adapted. You can see it's a glass building, the glass is used at this level. When you see from the floor level is different. At the face of the beam it has a darker band here, which is using a different glass combination, but the system is prefabricated, is called unitized curtain wall system or prefabricated panelized system. Each glazing panel you can see is prefabricated and is fixed to the building with the bracket here, and this is fixed with interlocking arrangement of aluminum extrusions. This is no limit on the extrusion shape, design. It is quite common to customize these profiles based on individual project needed. And in this video will explain you how it is moving horizontally. In our previous slide we have seen the building moving sway. When the building is moving on a sway, this will impact on the horizontal movement of these joints. And continuing with this, the movement when the building is moving, the engineer need to carefully check the joints. Unlike other building materials like concrete, wall, there is no primary joint on the surface except where it is interfacing. But curtain wall or glazing or cladding has lots of joints along the face of the building. Hence, the joint design is one of the critical here. The joints are needed mainly for building movement or thermal movement or for various natural conditions. There should be a good joint design so that the joints are not cracking or failing during the service of the building. And there should be two ways of doing a joint design, for horizontal joints and vertical joints. Vertical joints is mainly on the floor, horizontal joints on the panel joints. This calculation is showing how do we design a thermal movement. Thermal movement for any glazing system is primarily effect of change in temperature, which is delta T, and what is the width of the panel. So how wide is the panel? If the panel is much wider, and it has to move a lot of it horizontally, and the thermal expansion. So this simple formula here will show you the horizontal movement required for this curtain wall glazing system is around approximately 10 mm. Similar to horizontal design, it should also be checked for vertical design. Vertical design is critical if the curtain wall is going continuously to the tall building and it is passing several floors above, and it should be checked for two things: vertical horizontal movement and as well as inter-story drift. Inter-story drift is mainly from floor to floor. Drift is happening on the sideways due to the building sway. Lot of standards is allowing this, like h over 500. So floor height divided by 500, which the engineer need to be understanding this requirement so that he can design the joint such that it will not crack or fail during the building movement. And the joint design needed primarily for this factor. It could be due to the thermal, interstory, building design and installation tolerances, because it is most of the facade system, it is not a cast in situ, various components coming and is getting fixed at the site. So the engineer should be aware of tolerances. Floor deflection, the floor will be deflecting due to live load, or in some cases if the slender building, then the torsional may be a critical factors for a joint design. It is still, we are continuing with the joint design. Facade system has no definite rule for using a particular standard profile, unlike a steel design. In steel design we have a standard profile like a I-beam, C-channel section, angular section or a hollow section. But curtain wall, the engineer should be familiar with what is availability and what is possible, what is a limitation here. And you can see in this the profiles which is supporting the facade or system has no definite shape of the profile. It could be many different shape here. And the primary concept here is there is aluminum framing which is supporting the glass, and the glass is supported with a structural sealant, or it may be sometime has a mechanical fixing. And the shape of this aluminum profile could be very different from project to project, and each panel shape is defined by many different factors. It could be a open section like a C channel here, or it could be a hollow section here. We have just passed through the vertical joint design. This slide is showing the horizontal joint design. The horizontal joint design is primarily happening at the floor joint here, or it could be somewhere in between. And this horizontal joint generally happen, mainly it follows the floor slab of the or beam level of the building. And you can see this is the picture is taken on actual project site. On a curtain wall, this is a joint. If this is a floor here, what you can see, this U type of like a channel profile is fixed at the bottom. There is one more profile which is coming at the top. And what it does here is different panel is fixed, so it allows panel to move. As you can see in this video, the panels need to be moving vertical direction here, and this vertical movement will take care of that floor to floor movement. And you can see the panel here is not moving, panel above is vertically sliding. So it is it's called vertical joint design. Horizontal joint design, this is same detail as we have seen previously. The joint need to be taking care of same aspect, differential live load, floor deflection, installation tolerances. The horizontal, one more aspect is critical, is that creep or shrinkage and column shortening. This is a long term, these two are long term effects which will impact the framing elements of the facades. So the facade system need to be designed for joint design. Typically, if you combine all this impact, the engineer should be aware about 15 to 25 or 30 mm is need to be designed all the horizontal joints. So that will define how the joint design is designed for the project. There is multiple ways these joints are designed. It could have the capping here, it has no capping here, or is just exposed glass joint here. But the principle remains same here. There will be a joint here, the groove line joint here. You can see this picture has a different joint line here. It primarily allows the horizontal panels are moving, so that the glass panels or cladding panels not cracking due to the building movement. Another aspect of thermal movement that we have seen previously here is thermal movement design is, it is the same formula is adapted here, delta T times panel and thermal expansion. So the engineer should arrive and make sure he check for combination of floor movement and vertical movement. Factor of safety, as typical to any other steel design or concrete design, is applicable to facade elements being a glass, cladding, panels, or framing elements as a bracket detail. The safety factor is for a framing elements is generally a 1.5 times of safety factor, and for glass element the safety factor is much higher, like 3 or sometimes 5. It depends on the glass types or which standards is being used. The general design criteria, or we call as a best practice for framing elements. The framing elements on facades is generally aluminum framings. These 3 different types of loads is applicable here as dead load, mainly the glass panel or a cladding panel. Live load, just due to the glazing element or impact to the human load, or if it is used on a skylight, there are maintenance load, human loads to be considered, and wind load. Wind load for frame elements is given as allowable deflection criteria, span over 175 or 20 mm maximum, but again this depending upon where it is used for a window system, or if it is used on curtain wall system, this is different. And this is slightly less stringent as compared to a steel design. We generally span over 240. Aluminum has is much more ductile materials compared to the steel, hence the allowable deflection is given much more higher, so it's less stringent as compared to steel deflection criteria. And similar to the framing element, here it shows the glass and glazing element or cladding element. It has a dead load criteria. Mainly dead load criteria is not a major factor. It need to be checked for a live loads if it has a human impact, such as glazing used at the lower level, at the sill level or the hand railing, glass railing, this is critical. For wind load checking glass deflection, there is no definite control of the deflection. The reason being, deflection control is not something for a safety concern. It is more of serviceability, aesthetics, and a perception. So there's no definite control on the deflection, but as an industry practice is taken like a span over 90 or 25 mm maximum allowed. The span is considered as a shortest span, or whichever the span is the glass is deflecting.